So let's look at how linear equations and matrices are related to one another. Suppose we have equations for two straight lines. So here's two equations for straight lines. a11x plus a12y equals c1. And here's another one, possibly with different numbers here, for the a12 and the a22 and the c2. You might be more used to this form for the equation of a straight line, but these are actually equivalent. We could write this equation here as being the same as that one if we made the following choices. This for m and this here for the c. Anyway, with these equivalent forms here, we will work with these ones instead because they're going to relate better to our matrix ideas. And we note that we can rewrite these two equations here in this matrix form. So for example, if we multiply this top row here by this vector, we get a11x plus a12y equal to c1. And similarly for the lower row here, a21x plus a22y equals c2. So this matrix form here is entirely equivalent to these two equations. Or we could also write this in the summation form of matrix vector multiplication. If we write b1 instead of x and b2 instead of y, then we can write these two linear equations in this form, the summation form. Now, when we have linear equations in a matrix vector form here, then formally the solution, if it exists, is quite simple in matrix form. That is, if we happen to be able to work out the inverse of this matrix A, we have solved the equations. So to see that, if we multiply both sides here by a to the minus 1, and we remember that a to the minus 1 times a by definition is the identity matrix, and the identity matrix times anything is just what we started with, then formally then we have the solution. That is, we have the intersection point xy of these two lines in terms of the inverse of this matrix and these two coefficients that we started out with. So, solving linear equations and inverting a matrix are the same operation.
So there's a very important attribute of a determinant. If the determinant of a matrix is not 0, then the matrix has an inverse. And if a matrix has an inverse, the determinant of the matrix is not 0. So a non-zero determinant is a necessary and sufficient condition for a matrix to be invertible. Hence, we see that the determinant can really help us with our linear algebra. So what is a determinant?
The determinant of a matrix can be written using one of two notations. So this is one notation here, determinant of A, this det, and this is the other notation where we write out the matrix essentially in terms of its elements, but instead of square brackets we have just these straight lines. And these straight lines here do not mean the modulus of the matrix or some other similar use we might previously made of these straight lines on either side. There are two complete formulas we could write down for calculating the determinant. Those two formulas are equivalent to one another. One of them is Leibniz's formula, and the other is Laplace's formula. There are also many numerical techniques for calculating determinants, and we're not going to give any of these general methods here, although we will give an informal version of Leibniz's formula as we go forward here. So let's look at the determinant of a 2 by 2 matrix. So for our 2 by 2 matrix, which we can write out here like this in its determinant form, the answer to the determinant is a11, a22 minus ee12, ee21. That is, we're adding the product on the leading diagonal of these two numbers here and subtracting the product on the other diagonal. That is the product of these two numbers here. For a 3 by 3 matrix, it gets a little more complicated, and there are two rather different ways of looking at this. So for our 3 by 3 matrix, we can write the determinant with these two notations here, and one way of multiplying this out is shown here. So that would be ee11 times ee22 times ee33 minus ee23 times ee32. And then that term has a positive sign. And then the next term we would evaluate would be ee12 times ee21 times ee33 and minus ee23 times ee31. So ee12 multiplying all of this here. And we see we're always getting a positive contribution and a negative contribution. And this term also has a negative sign overall. And finally, for our third term down here, we've got ee13 times the sum of ee21 times ee32 minus ee22 times ee31. And this term here would have a positive sign. If we take the expression we just were looking at and wrote it out in one line, and then multiplied out all of the terms in the brackets, we would see the following. We would see a collection of terms, each with 3 elements multiplied together, some with minus signs and some with positive signs. Here's another minus sign. Each term contains a different element from each row. So this term here that we're looking at, which is this one up here, contains the second element from row 1, the third element from row 2, and the first element from row 3. And if you look at all of these different terms here, you will find they have the same characteristic. They contain a different element from each different row. And the elements in each term are never from the same column. That's kind of confusing when we look at it in words, but as we look at this a bit more graphically, it will become somewhat clearer what we're talking about. We do always have one element from each row and each column in each of these terms. So there's an element from row 1 here, an element from row 2, an element from row 3. There's an element from column 2, there's an element from column 1, there's an element from column 3. So this suggests to us what the general form of a determinant really is. And we'll illustrate this with the 3 by 3 determinant again. So this form that we have written out here, as we said, contains every possible term with one element from each row, with each element being from a different column. And this is a general property of determinants. To understand how to construct a determinant, it only remains for us now to find the sign of the different terms we have to put in. And again, this becomes clearer when we look at it graphically. So to do this, what we're going to do is we're going to count the number of row swaps we have to make. This also works for column swaps, to get all the elements in the term onto the leading diagonal. And if that number is even, the number of these row swaps or column swaps we have to do, the sign is positive. And if that number is odd, the sign is negative. Okay, so understanding that in words is really very hard, but let's look at it, as I said, graphically. So let's look at this term here, one of the terms in our chain of different terms that we have to add and subtract to get the determinant. So that term is the one that corresponds to these black numbers in our expression here. And I've made all the other elements grey in this diagram. So if we swap this row and this row, then we find that we have managed to get all of these black elements on the diagonal. So we can say that in order to get this term so that all of the elements are lying on the diagonal, we have to perform one row swap. 1 is an odd number, so the sign of this term in the determinant is going to be negative. On the other hand, for this term here it is before we do any row swaps. We've got one of our elements here, one of them here, and one of them here. If we swap these two rows round, then we get the determinant into this form. But that still does not have all the elements down the leading diagonal. But one more row swap, swapping these two rows about, will achieve that for us. And here we are. So performing 2 row swaps will end up with all of these terms that we want to multiply together, all lying on the leading diagonal. So we had to perform 2 row swaps in this case. 2 is an even number, so the sign of this term in our overall sum will be positive. And this is how we make up the determinant. We consider every one of the possible ways in which we can choose one element from the first row, a different columned element from the second row, and a different columned element from the third row, and so on if we had more rows in our determinant. And then we figure out the sign of each of these terms by figuring out the row swaps. And the answer to these row swaps is unique, by the way. There are many different ways in which we could do the row swaps in order to get the answer sometimes, but the number of them would remain the same. And incidentally, this way of looking at the determinant is actually Leibniz's determinant formula. So I won't try to write it out for you. It's not very clear when you write it out either. But thinking about it in this graphical fashion lets us see what the formula really is.